Good day, and welcome to Africa Teen Geeks. This is a STEM digital school. If you have just joined us in here, you are in the grade 12 physical sciences class. My name is Nonkululeko Madondo, and I am your teacher for grade 12 physical sciences. Yes, we've indeed come a long way with physical sciences grade 12 here on Africa Teen Geek. So basically, what's going to be happening for the next few weeks, we're going to be doing a whole lot of revision just to bring you guys closer to your exam and your exam dates, okay? So what I did today is I decided that our lesson is going to be basically, we're going to be doing revision questions using exam questions for paper one, okay? So what we're going to be doing, we're going to be reading questions, seeing how we answer them, writing step by step on how we answer, and just to make sure that we're grasping the concepts of what is needed when you're writing your answers in each and every exam. Okay, grade 12s. My name is Nonkululeko Madondo. I am your teacher for grade 12 physical sciences. There's a whole lot of past papers, but I've basically done a bit older papers like the 2012, 2013, 2014, because during our lessons, we've been doing a whole lot of, the recent examinations like 2018, 2017, and 2019. So I thought to go back just a little bit so that we can find questions that we haven't been dealing with recently. In that way, we can be able to start doing our revision based on that. So I've compiled questions from different papers, different exams, and different areas. So I hope that everybody is going to be, participating, and you'll be understanding. And I'm reminding you guys that in this classroom, we do not do voiceovers. I'm the only voice that speaks. But if you have any questions that you want to know, you can go straight to the chat box and send me a question. If there's somewhere where you're getting stuck or you don't understand, you can let me know there, and I will go back and explain. The main point here, the main point for this class and what we're doing here is for you guys to understand what is going on, to know the work thoroughly and know how to answer it. So the aim is not for us to finish up quickly, but to make sure that we go through everything effectively and consistently. Okay, guys. So nonetheless, let's get started. So we know what do we need to know? You know, with the CAPS approved, you can even check on the guidelines. Basically, there's a lot of things that we have there. We have the work energy and power. We've got the vertical projectile motion. We've got the Doppler effect. Then we've got electrodynamics, which has the electrical circuits and all those other stuff. So, but you're going to see them as we're working through. And basically, what you need to know as a grade 12 learner is to identify when you read a question. The questions are not going to be written, for example, this is a Doppler effect question, or this is the work energy and power. You, as a grade 12 learner, need to be able to identify just from reading a question what topic it's based, which equations go with it, okay? So you need to be able to do that, because in the exams, you're just going to have questions. They're not going to write that, oh, this is this part of the syllabus, this is the work, energy, and power, or this is the forces, this is the work done. No, they're not going to do that. They're just going to write questions. You, just by reading through certain guidelines, you're going to have to be able to identify them. So question and exam questions and step-by-step answers is what we're going to be getting on today. Okay, I hope that everybody has you all have your books and your markers and your calculators ready. We're going to start with the first one. Okay, so vertical projectile motion is actually a topic that we also started with as we were doing our revision. What do we know about vertical projectile motion? This is term one work, right? So when you just have a few keywords that you have to look at. So with vertical, we know is the up and down directions, velocities, movements, motions that move up and down. Okay, so basically you'll have something like this. Okay, so this shows you that here we are dealing with a vertical projectile moment because it's a vertical movement or motion. Okay, so this one we're going to start with this question. This is a question from the February-March 2012 paper one. Okay, so it says here, a stone is thrown vertically. So that's the first step that already you know. Here we are dealing with vertical projectile motion. So once you get that right, already you know the kind of equations that you're going to be using for this one. So this is your first keyword that you write on your given. A stone is thrown vertically upwards at a velocity of 10 meters per second. So what do we have here? This is going to be our V initial, right? So we're already writing what is given, which is 10 meters per second. Okay. And then from the top of the tower at a height of 50 meters. So the height here, the H is equals to 50 meters. Okay. And then after some time, the stone passes the edge on the tower and strikes the ground below the tower. Okay, so they say ignore the effects of friction. So now we know the few keywords, the most important parts is that it's thrown vertically upwards. So this is the first part that we need to know. The second part is the velocity of 10 meters per second, the height of 50 meters. So these are all stuff that is given, okay? And it strikes the ground. So you know the minute it strikes the ground, that velocity there is going to be equals to 0, and you ignore the effects of friction. So there we have it. So this is a sketch. Luckily for us, it's already given, and we have a window there somewhere in that building. But for now, let's just get out of the way what we need to know, okay? So the acceleration here, it's going to be minus 9.8 meters per second, -1, right? -2. Okay, and we can always say we take upwards as positive. Okay, so now for now, we've labeled out all the stuff that we need to know before you even attempt the question. That's why I say that what's important when you write your exam, you need to understand what kind of problem are you dealing with? Are you dealing with projectile motion? Are you dealing with work, energy, and power? Are you dealing with forces? You need to be clear on that. So that's why it's very important that you understand your question, especially with mechanics. Most of them, they use similar equations, but there's those ones that stand out where you know this is what you always use. Like for example, with vertical projectile, our acceleration will always be 9.81. Whereas if you had other if you're working with forces that are being pulled, etc., there you'd have to calculate your acceleration. But this one, because here it's a vertical one, we work with acceleration, and our acceleration equals our gravitational potential, which is the 9.81 meters per second -1. Okay, so now that you've got all of that, so let me just, oh, no. Just erased everything by mistake. Okay, so this one is, you always choose the direction, right? So we choose upwards as positive, and our acceleration is minus 9.8 meters per second squared, or you can say minus 9.8 meters per second -2. Okay, so now we're going to start with the first question. It says here on 1.1, draw a labeled free body diagram showing the forces acting on the stone during its motion. Okay. So what is that going to be? So here, there's only one type of force that we have, okay? And it's the force of gravity. So how are we going to draw our free body diagram for 1.1? Our free body diagram, it's going to just be a single straight line. And then we're going to write there force of gravity. And you need to, you see, once you write a force diagram like this, you need to be able to explain what this FG is, because it's a force body diagram. You need to explain all your points that you're working with. Okay, so this is your force diagram. And what are we going to have it as? We're going to mention there that FG is the force of gravity acting on the stone. Okay, so this is your answer for 1.1. Okay, so that's what we're going to have for 1.1. This is our force diagram. I'm sorry, I'm not a good drawer, but I hope that this makes sense to you. So this is our force body diagram, because we only have one force, and that's the gravitational force that acts on the stone, and that is going to be the force of gravity, or we can even say the force of the earth. Okay, so that's the earth's pull. Okay, so that's the first answer right there. So now moving to the next one. So you see how simple it is to get yourself 2 marks for free just by drawing. That's what you need to do. So if you draw the sketch alone, you won't get the full 2 marks. You'll only get 1 mark. So it's very important that you understand that in physical sciences, everything that you do needs to be explained. You explain each and everything that you do. Okay. You assume that you are writing to somebody who doesn't understand physical sciences. So you need to be able to teach whoever is going to be marking your paper. Okay. So moving on to the next question. It says here, calculate the number 1.2.1, the time taken by the stone. Let me just make some space here. Calculate the time taken by the stone to reach its maximum height above the ground. Okay. I'm sorry, I'm just trying to see if there's no place that I can write. And oh, I'm just trying to see, guys. Sorry, I'm just trying to see if there's absolutely no way for me to write and it stays on that same spot. Okay. Okay, there's absolutely no way. So everything has to be erased from here. Okay, at least we've got that out of the way. So I'll have to just work on the spot. Okay, so for 1.2.1, it says here, the time taken by the stone to reach its maximum height above the ground. So what height are we looking for? Maximum height above the ground. So for maximum height, it's from here to here, right? This is the maximum height, right? So we're looking for this spot all the way here above the ground, okay? So this will be our maximum height. So this will be our maximum height. Okay. So we've got our height, which is this one. the 50 meters, but now we also have a maximum height. So how are we going to work this out? First, what we can do, let me just draw a small sketch. Let me just erase here. Okay, I'm just looking for a clean page that we can work with. So here, what are we looking for? Number one, maximum height above the ground. Okay, so 2.1, 1.2.1. Okay. Okay, so this is how our sketch is going to look like. There we have it. This is the maximum, right? So this is our 50 meters building, right? And then what we know is that from the initial part, when the stone is thrown up, it's at 10 meters per second, okay? And then it goes down after here. When it reaches the maximum height, it goes down, right? So what are we looking for? There we have it right there. We're looking for the change in time for the maximum height, right? So first, what we need to do when we have a question like this, we need to write what is given, okay? In this case, what is given? We have your vertical velocity of 10 meters per second. So we've got our V initial, which is equals to 10 meters per second. And we've got our final velocity. It's going to be, what's our velocity when we're here on the ground? Remember, stone falls on the ground. So here, our final velocity is going to be 0 meters per second negative 1. And then we've got our acceleration, which in this case is minus 9.81 meters per second negative 1. We can just say 9.8 just for workout purposes. So what are we looking for here? We're looking for our triangle T. We're looking for our change in time. Okay, so what equation are we going to use? Okay, so here we're looking for the maximum, oh no, not maximum height. Sorry about that. We're looking for the time taken. We're looking for the time taken by the stone to reach its maximum height. Okay, so I just made a mistake there. Time taken. Okay, so here we are working with the time taken to reach maximum height. Okay, so always read your questions many times, just like you see how easy it is for you to actually look for the wrong thing. If you're not sure, always go back to the question and check what is it that you're looking for. So here we are looking for the change in time. So what are we going to do? Which formula are we going to use? Remember, we've got all the formulas together, but which one has change in time? We can use this formula that says final velocity is equals to initial velocity plus acceleration times change in time. So this one is, I think this is the most basic formula in this type of questions, okay? So here it's going to be 0 is equals to 10, which is what we have as our initial velocity, plus minus 9.8 times change in time. Okay, so what do we want? We want we are looking for time, so we need to make time the subject of the formula. So how are we going to do that? Here we're going to take this 10 here and take it to the other side, which is going to give us minus 10 is equals to minus 9.8 times change in time. Okay, so now to make change in time the subject of the formula, it's going to be minus 10 divided by minus 9.8. So already these two are going to cancel each other out, the minuses, and you're going to have this, and our change in time in this case is going to be 1.02 seconds. Okay, so this is our time taken to reach the maximum height. Okay, I hope everybody's following, because if you do not understand, please make sure that you let me know so that I can go back and check the work for you again and explain wherever it is that you're getting stuck. Okay, so that is our answer for this is our answer for 1.2.1, the time taken. Okay, so you see what I told you guys, it always makes sense when you know if you know how to identify which part of the syllabus your question comes from. Because if you don't know that, you're going to have a big problem. You won't be able to understand. If you don't understand the section, you won't know which formulas apply to that section. Okay, so now we go to number 2.2. Let's see what they say there. It says here, now they want the maximum height that the stone reaches above the ground. Okay, so basically here, what they're looking for, if your stone is thrown from here, right? This is where your end of the building is. If you throw it from here, it goes up and then it falls down. So what do they want to know? They want to know the maximum height the stone reaches above the ground. So they're looking for this portion here. So this is going to be your triangle Y. That's the portion that they're looking for. Okay. So let's go and try and so now that we can draw again, once again, our little diagram that reminds us what it is that we're doing. Remember, we're going like this and then we're going down. It's always good to use this when you're working with your maximum heights. So now, first we had our change in time. Now we can look for our change in Y, which is this part from here to there. So now we're looking for the maximum height. We're still on 10 meters per second minus 1 for the maximum height. I mean for the maximum, for the initial velocity. So here on 1.2.2, it says now they're looking for the maximum height. Okay, so how are we going to find the maximum height? First, as usual, we're going to have to find a formula that has our change in Y. So what do we know about our formulas? We know that there's the one that says change in Y is equals to initial velocity times change in time plus a half a triangle T squared. Okay. So here basically it's all about substitution. We already know because we know all the given. We know that our This is what we're looking for. Our initial velocity is 10, as we have it there. And our change in time we've already found, which was 1.02 seconds plus a half minus 9.8 times 1.02 square. Okay. So we've substituted everything that we have, and now we can find the answer. And the answer in this case, okay, when we take these two, 10 times 1.02, okay, no, I don't want to use this formula. Okay, why don't I want to use this formula, guys? I want us to check something out here. I prefer that we use the formula that says VF is equals to VI plus 2A change in Y. And why is that, guys? Let's just look at this two formulas. This is the first formula that I tried using, and this is a second formula that I'm suggesting that we use. Why is that, grade 12? Just think, why would we have to prefer this formula over this one? It's quite simple, hey? Why? The first question that was given to us was for us to calculate time. So which means that the time that we have here is the time that we calculated. But on this formula, we do not have time. So what is the problem with a formula like this? What if the time taken that I have written here is wrong? Then, which means that everything else that I have written is wrong. But if my time is wrong and I do number 2 using this formula here, it means that I will still get some of the marks. I will be able to get marks for my second question of the problem. So make sure, guys, that you use what is given, most importantly, more than you use what you got calculated. So like this one, we calculated the time, so it's better not, it's not preferable, because what if I calculated a wrong time? What if I got 3 instead of 1.02 and I start substituting it for this y? Everything is gonna be wrong. So it's better to use a formula that doesn't have anything that I needed to calculate. Okay, so now let's go back and use formula number 2, which is actually formula number 1. When you check on your, oh goodness, no, this virtual pens. Okay, so we're going to be using the VF is equals to VI squared plus 2A change in Y. So here, our final velocity, we know they already told us, because the stone falls down. So when it falls down, there is no velocity, it's 0. So that's why our final velocity is 0. And then our initial velocity is going to be 10 plus 2 minus 9.8 change in triangle Y. Okay. So what are we going to have here? We're going to take this one and we take it to the other side. It's going to be a minus 100 is equals to minus 19.6 triangle Y. Okay. So what our triangle Y is going to be equals to 5.10 meters. Okay. So that's only the change, because here, from here to here, it's the change, but we're looking for the maximum height above the ground, and the ground is here. So they want to know from here to there, what is our height? What do we know? We know that this one from here to here is 50 meters. And then now we can add it to the change there to find the total height above the ground. So the maximum height in this case is going to be equals to 50 plus 5.10. And that is going to give us 55.1 meters above the ground. Okay. I just hope that you guys have a better handwriting than me, but I think it's a virtual pen that's making it a bit jibby. But if you do, make sure your work is as clear as possible so that it doesn't give the markers a problem whenever they have to mark your work. Okay, you need to make it easier for them to mark. Otherwise, some of them are tired. They've been marking for hours and hours. They might just give you wrong if they don't understand if you have a 5 or a 6. Okay, so make sure that you got your numbers right and your handwriting right as well. I know you'll be tired and trying to work fast, but you need to do it right. Okay, so that is the questions that we've had here for our vertical projectile motion. We'll probably come back to some of them again. We just have to now go back to the rest of the problems that we have for today. Okay, so moving on to the next one. Now we're going to be doing a short revision on the work energy theorem. Okay, remember the work energy theorem is a part where it deals with work energy and power. Is a term, I think it's term 2 work. Yes, it is term 2 work. Okay, wait, we're not done here. Oh yes, we're not done. I just ended it here. I just ended it on 1.2.2. We still have 1.3 and we still have the others that we need to do. So what do they say on 1.3? They say they're using the ground as reference. And yes, indeed, we always use the ground as reference unless otherwise stated, unless they tell us that no, use the window as a reference or use the top of the building as reference. It's very important that your reference is according to what is stated. So that's the most important part, that we are using the ground as our reference. So our reference starts from here. Sketch a positive time graph for the entire motion of the stone. Okay, so basically here, if we have to draw a graph, we can have our graph like this. This is our y-axis and this is our x-axis. Okay, so this is our x-axis. Make sure your graph is neat and you have a ruler, unlike me right now. So this is our ground as reference, right? And then we're going to have our height and we're going to have our maximum height. So this is going to be our 50 and that one there is going to be 55.1. Okay, so this is it's a height in meters and this is a change in time in seconds. Okay, so what are we going to do? We're going to draw it from there because that's where our stone was thrown from, and then it's going to go up, 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 and down. Okay, and then here we're going to have our maximum time, which is 1.0 1.025 seconds. So this would be a graph that explains basically what is happening and everything else that we've calculated. Okay, so this will be our question 1.3. So this is how our graph would look like, but hopefully you guys will be able to write it neater and you'll have all your marks, just as simple as that. Always need to know, whatever graph that you draw, it needs to be able to explain your point. Nobody needs to ask, so what is this line for? No, this one you can see, it's the height in meters. So if you check here, it's the time in seconds. There's a, what's this? This is looks like a maximum time because it's on the highest point, okay? And this is where it started. It started at 50 meters above the ground. And it went up to 55.1 meters above the ground. And then it slowly went down after that. So those are all important things that you guys need to know when you draw and basically when you try to understand what how to express or explain your problem. Okay, because basically that's what you do, guys. When you're writing an exam, you're basically explaining the work to your examiners. Okay, so now we're moving on. They say here, on its way down, the stone takes 0.1 second to pass a window of a length 1.5. Okay, so from here to here, it's our 1 second. It's our 0.1 second. So from, because you said it moved. From here, remember it went down. So from here to okay. So from here to there, it's going to be 0.1 second to pass a window of a length of 1.5 shown on the diagram. Calculate the distance y1 from the top of the window to the ground. Okay. So now this is a very tricky one, but it's doable as long as you understand your concepts and you understand what is happening. Okay. So we're looking here for y1, right? So that is what we're looking for. And here they say, we need to make a short sketch. Let me just delete this. Let me just erase here and get us a clean page. Okay, so now this is what we have. We still have our sketch, right? We still have our building. And right here in the middle of our building, we have a 1.5 meters. A 1.5 meters window here in the middle. And we still have our stone that has fallen down. And our y1 is going to be from here to here. And this is going to be our y1. Okay. Do you see where y1 comes from? From the top of the window to all the way down. Okay. So now we're going to see which formula is best to describe. Let's see what we have. First, we have our initial velocity, which is what we're looking for. Of our initial velocity is a 10, right? Let me see. That's our initial velocity from here to here. But the initial velocity from there to there, we do not know what it is, right? So what is our final velocity? Vf is also a question mark. What is our final velocity? We've got no idea. Okay. And then what else do we know? Is that our acceleration is equals to minus 9.81 meters per second, -2. Okay. And then we also have our change in time, which is equals to 0.1 second. Okay, so this is what is given. And we have our change in y, which is equals to 1.5 meters. Okay, so from there, we need to find this one first, right? So how are we going to find this one? Here we're going to say the change in y is equals to vi change in t plus a half a t squared. Okay, we chose this one because it's the one formula that has our change in y and our vi together. Okay, and we do not have our final velocity, so we wanted a formula that will not have the vf because we do not know. We don't, otherwise we'll have two unknowns that we won't be able to solve. It might take a whole lot of simultaneous equations to do that. So this one was a beta option. So we know here that it's minus 1.5 meters, right? Remember, we chose our upwards as positive. So if our upwards is positive, this one is going down. So going down will be a minus 1.5. And we're looking for the VI. And our time is 0.1 because it's given. Okay. So plus half minus 9.8 times 0.1 squared. Okay. So our velocity, our initial velocity, because we're going to take this answer, we're going to take it this side. It's going to be a minus, and then we're going to divide it by 0.1. Our initial velocity is going to be our 14.51 meters per second. Okay. So from there, let's just go back. Always need to go back and reference the question. On its way down, the stone takes 0.1 to pass the window length of 1.5 meters as shown in the diagram above. Calculate the distance from the top of the window to the ground. So we're still looking for this y1 here. So now we've got our initial velocity here. Okay. Okay. So now we're going to go to this formula here. Vf squared is equals to Vi squared plus 2a change in y. Okay. So now, because we've got a velocity here and a velocity there, we go back to our original one where our vi is equals to 10. And if it's this side, this is our final velocity, which is vf. Okay. So we already calculated that, which was a 14.51. Okay. So it's going to be minus 14.51. And why do we have it as minus? Because we chose our positive direction to be the upwards motion, and this one is a motion that's going down. Okay, is equals to 10 plus plus 2 times minus 9.8 times the triangle y. Okay. I forgot to put a square there. So you bring this to the other side. It's going to be minus 14.51 squared minus 10 squared is equals to 19.6 minus 19.6 triangle y. So you can do a quick calculation there, and let's see if you get the correct answer. Okay. Okay. So while we're substituting there, let me just put it this side so that we can see. Then we're going to have our triangle y is equals to minus 14.52 squared minus 10 squared divided by minus 19.6. So here, I just wrote it like this. It's better, so then you can just plot it on your scientific calculator the way it is. And your answer there should give you change in y is equals to minus 5.64 meters. Okay. So there we have our triangle y. So let me just draw a line here so that we can be able to see the next one. So what is our y1 in this case? Remember, now we've calculated the distance of this one right here. So our y1 is equals to 50.50 minus 5.64. Okay, so that will be equals to 44.36 meters. Okay, guys, I hope that all of this is making sense to you guys. I know mechanics is quite a challenge, but with a lot of practice and a lot of problems with many question papers, you will get it right. It's very understandable once you get it. It just needs some time for you guys to understand. But if you do not understand, you guys can let me know at any time so that I can go back and explain wherever it is that you're getting stuck. Okay. So that's the end of that problem. Okay, I'm just trying to erase everything. It takes time. Okay, so now we're moving on to the next problem. I think this was the end of this one, right? That was the last of the problem. Guys, I hope that you guys are understanding this work and you're slowly starting to understand what is going on. Okay, so now we're moving to the next problem at hand. We're moving to the work energy theorem. Okay, so we're working through all the mechanics problem, all the paper one problems. So like I told you guys, these topics, like this one that's written here, is not something that you're going to be told. They're just going to give you a question and you're going to have to figure out what kind of a question it is. So like this one, you have to know here already we have a mass on a smooth across horizontal constant velocity. So we have a constant velocity. So V is equals to 12. Okay. The biker applies brake. So the minute you see this, you know that now we've got force, friction, right? Which exerts a force of on the motorbike, causing it to come to a stop. Okay. So those are the few hints that you already have here. So what they want to know here for the first one on A, what was the net work done on the motorbike while traveling at a constant velocity? Okay, network constant velocity. So let's go and okay. I just want to write it on top so that we know what we're looking for here. So here they say they want the number one net work done at constant velocity. Okay, so that's what they're looking for. So we're going to go back and see. We're going to write what we have. Okay, so here we've got the mass. The mass equals to 800 kilogram. Then we have the velocity. Velocity at 12 meters per second. And then we have the frictional force of 2,500. Okay, I don't know. Yes, sorry about that. The force friction, which is equals to 2,500 Newton. Okay. So let's go back to the question and what the question wants. It says here, what is the network done on the, what is the network done on the motorbike while traveling at constant velocity? So let's see how we work this one out. So number A, we're looking for the net work done. So A, the network done, what do we know? The conservation of energy, it says the net work done is equals to the change in kinetic energy. Okay. And that is going to be equals to the final EKF minus EKI, right? And then from there, we're going to substitute. It's going to be half mv f squared minus half mvi squared. Okay. And that's going to be a half 800 0 at constant. Remember, at constant velocity, our final velocity is 0 minus the half 800, and vi is going to be our 12 squared, and that all is going to give us 0.0 minus 57600, and that will give us all of this will be equals to minus 57600 joules. Don't forget the standard, the SI unit, all the time. You need to have it there, okay? Otherwise, if you don't have this, you're going to lose a mark, okay? So you must have it like that, okay? So that is our work net. So our work net is equals to change in kinetic energy. And guys, remember, you determine this by what you have. If you were given a distance, and if you were given, for example, a distance, if it wasn't velocity that was given, once you have velocity, that's when you use your kinetic energy formula. But if they had given you, for example, the distance, then you would say you would use work net is equals to F triangle X cos theta. So there's always different ways to find your answer depending on what is given. Okay, so this is going to be our A. So now we're moving on to the second part. The second part is number B. Number B says, let's go back and see what number B says. It says, what was the net work done on the motorbike while braking? So now we're adding the force that's acting against, because for a car to stop, there needs to be a force that is working against there needs to be a force that is acting against the object, right? So in this case, okay, let's go and check it out. Okay, what was the net work done on the motorbike while braking? Okay. Oh no, man, I think I made a mistake here. What was the net work done while traveling at a constant velocity? Ooh, guys, I'm sorry. Teacher has made an error. Here for number A. For number A, at constant velocity, let me just try and sketch it out. If your motorbike is traveling at a constant velocity, this is you driving the motorbike. That's why I did science and not drawing. If the velocity is constant, it means that VI is equals to V final, right? Because it's constant, it doesn't change, doesn't go up and down like the normal ones that we know. So these ones will both be equals to 12 meters per second negative 1. So which means that at A, our network is going to be change in EK, and our change in EK is going to be equals to half mv f squared minus half mvi squared. This is going to be equals to half 812 squared minus half 812 squared. Why? Do you see here? They are both the same because they are both equal at constant velocity. And this is going to give us an answer that's going to be 0 because everything's the same and it's got a negative, right? So this is going to be our 0 joule. So no work will be done at constant velocity. Okay. So now moving on to number B. They've asked something else here. It says there, what is the network done on the motorbike while braking? Okay. So while braking, it's no longer at constant velocity. Why? If it was constant, it would still be going on 12 meters per second. But for it to brake, it means that it's slowly, the velocity is slowly decreasing. So there's a force that's acting on the motorcycle that's making it to slow down. And when it slow down, it's no longer constant, it's changing. Okay, so it's no longer at constant velocity. So now for number B, our network is going to be equals to change in EK once again, because we're working with kinetic energy. We've got velocities. So this is mv final squared minus half mv initial squared. Okay. So what do we know? Okay. Let me just write notes on the side. What do we need to know about this condition here? On the first condition, we had a constant velocity, so which means that VI was equals to VF, okay? So that gave us 12 meters per second negative 1. In this case now, they're telling us that the car is braking. What does it mean that, number 2, when a car is braking, it means that it's slowing down. But what is the end point? It means that our final velocity will have to be a 0, because at the end of the day, it has to stop. Like they mentioned here, they said on the motorbike, causing it to come to a stop. So once a car comes to a stop, it means that our final velocity there is going to be a 0. Okay, so that's what I'm saying there. So here our initial velocity VI is going to be the 12, because it started with 12, but now it's slowing down up until it gets to a 0. Okay, so we come back to the formula now. We're going to substitute what we now know. Okay, so half 800, our final is going to be 0, like they've already told us, minus half 800 12 squared. Okay, so this is going to give us a 0 minus 57,600, sorry about that. And that's going to give us a minus 57,600 joules. Okay, then we come back and we try to figure out, why is our answer negative? The answer has to be negative because now we are dealing with a frictional force, a force that's acting against the motorcycle. So for the force to be effective, it needs to be opposing. They cannot be all on the same, they can't both be positive. So one has to be negative. So if your motorbike was moving on the right path, your frictional force will be on the negative path. So which means that they will always, the applied force and the frictional force are always in opposite directions. Okay, so that's why our answer has to be negative, because our frictional force is acting against the motion of the bicycle, the motorbike. Okay, I hope that makes sense to you guys. So that is our answer for number B. Then now moving on. We move on to number C. What do they say on number C? It says calculate the distance the bike traveled while braking. Okay. Traveled while braking. Okay. So it means in this case, what we have is our motorbike there with a person. So it's moving at constant velocity. And then from here, it starts braking, right? A certain point. So we're looking for this X point. The change in X, okay. So on number C, what do we know? We know that our force is equals to, our frictional force is equals to 2,500 Newton. Okay, so when we calculate the net force, what do we know about the net force? We know that our net force is our net force, our net work done, our net work done is equals to the sum of all forces acting parallel to the distance, okay, of applied force. Okay, do you still remember this term, right? So what are we going to have? If this is our sketch, like I mentioned, this is our motorbike and it's moving straight. There we have our 12 meters per second. So our work net done, what we know about our work net done is that work net in this case will be equals to the work of braking, of the braking force, plus the work done by other forces. So what is our work done for our braking force? Okay, we've got our work net, which is our minus 57,600, and our work braking, this one we don't have it, okay? Plus the work done of other forces, we know that it's 0 because there is no other forces that were mentioned. So you do not put in what you not mentioned, okay? So you can't just out of nowhere start creating your own forces. We only deal with what is given, okay? So working through that, we're gonna have to find the work braking, right? The work while the motorcycle is braking, and that's going to be F triangle X cos theta, right? And like we said there, remember I said work net is equals to work work braking plus work other forces. So here's going to be minus 57,600 equals to work of braking and other forces is going to be 0. So work braking is going to be equals to minus 57,600, okay? Okay, so that's the work done for braking. So now we're looking for this distance, right? This is what they're asking us for. They're asking us for the distance while it was braking. So we're going to have our minus 57,600 is equals to the force, which is 2,500 change in x, and what is going to be our cos theta? If this is our direction and it's moving this way, this is going to be 180 degrees, right? So this is going to be cos 180 degrees. Because why is it 180 degrees? Because it's opposing. Okay, so if it's moving left, now it's moving right, and for that to happen, your angle needs to be 180 degrees. Okay. Okay, so that's the answer for number B. Okay. So that's how we found our. Now we have to look for the change in X. Our change in X is going to be minus 57,600 divided by 2,500 times cos 180 degrees, and that grade 12 is going to give us an answer of 23.04 meters. Okay, so this is your answer right there. Okay. Moving on to the next one. I hope that you guys understand. So you see how simple it is. You just need to know how to apply what you need to apply. I mean, you could have easily struggled to find the work for the braking, the work done when the car was braking. But if you remember that the work net is equals to all the work done of all the individual forces, which would be the work done while it's braking and the work done of other forces. But in this case, we do not have other forces that was given to us. We only have the braking force that was given. So that's why it will be equal to the net force. So the net force is equal to the braking force, okay? And then once you get your braking force, now you can use the formula. Remember I mentioned earlier on that your formula depends on what is given. In this case, you're looking for the distance. If you're going to look for the distance, then it has to be, you have to use this formula right there, because the one of the kinetic energy does not have distance, okay? I hope that we are together. Grade 12, you guys really need to work on it, especially with the physics. I know the physics has got too many calculations, but I feel they both equal weighing. So you need to make sure that you get your answers right. Okay. So this is the first step. It's got quite a lot of marks just doing this. So make sure that you understand. You understand what you're doing. Okay. So that was our number C, where they asked us for the distance. Okay. So that was distance, the bike. Okay. So now we're going to move on to question 2. Question 2. Okay. Question 2, they ask, it says that an object it's a different kind of question now. It says an object is pulled at an angle of 30 degrees, okay, to horizontal surface with a force of 40 Newton. Okay, so we're already having our given, right? On number A, our given, we've got an angle of 30 degrees, and then horizontal force, which means the force applied is equal to 40 Newton. The frictional force, the force friction is equal to 12 Newton, and the object travels a distance of 3 meters under these conditions. So we've got our distance, which is our change in X, it's going to be equals to 3 meters. Okay. So the first part that they want is they want us to, on A, they want us to calculate the work net, right, on the object. So what do we know about the net work, guys? Come, now we can start our problem here. What do we know about the work, the net work? We know that the net work is a sum of individual forces that are acting on an object. I think I wrote it on the previous question as well. So for example, with network, with the network, it would basically be force 1 times triangle x cos theta plus force 2 triangle x cos theta, right? So this is basically up until, depending on how many forces. If you have other forces, you're also going to add them. If you have force of gravity, you're also going to add it. So basically the list goes on until you mention all the types of forces that you are working with. So let's draw a sketch quickly on how our problem looks like. So there we're going to have it on the ground. There is our little box there. And we've got the, remember they spoke about at an angle of 30 degrees, this force is applied, pulled. So you're pulling, so which means that they both go in the same direction. This is 40 Newton, okay? And then we also have a frictional force, which is acting on the opposite direction. The force friction is going to be equals to 12 Newton, okay? And we also know the distance from here to a certain point is going to be changing x, which is equals to 3 meters. Okay, so what they want to know, they want to know the work done. So our work net, our net work done is going to be the work of the frictional force plus work of applied force. And that is going to be equals to F friction triangle x cos theta plus 40, oh sorry, plus F applied triangle x cos theta, and that our frictional force is given as 12, our triangle x is 3, and this is going to be cos 180 degrees. Why is it 180 degrees? Because it's exactly 180 degrees out of phase from the applied force. Okay, so which means that we're going to take a certain component, you see. So because this is going that way, we're taking a component that is there. That's why we're using cos 180 plus force applied is going to be 40 times 3 times cos 30 degrees. So that has already been given to us, right? And all of this is going to give us 67.92. Oh God, sorry about that. This is not pretty audible. Can say this is equals to 67.923 joules. And there you have your answer. Okay. So that's basically how it is. I'm sorry, this shouldn't be there. Let me just come back. So remember, it must be parallel to this. So this one is going this way. It's 180 degrees because it's 180 degrees out of phase from this distance there. So this one is at an angle of 30 degrees. Okay. Hope it makes more sense. Always make sure that you read your theories, guys. I know calculations, you must focus on practicing a lot of calculations, but it will really help you to do some theory so that you understand where the concepts come from. What does it mean when they say the distance, the forces, you only take the forces that act parallel to the distance. Those stuff is important, and you get them through reading much of your theory questions. Okay. So we're moving on now. We're moving to a Doppler effect. Okay. So you see, we're going on through the terms according to the terms as they've come. Okay. So we're moving on from mechanics to the Doppler effect. This is the Doppler effect. Sorry about that. So you see, I've written everywhere where it's been taken from the Department of Education, November 2012. There's many problems that you can get, guys. There's 3 types of papers that you can get that are written by the DOE, the Department of Education, Basic Education. You will have there's March papers, there's February, March papers for the people that are supplementing for December. There's June papers, and then there's December papers. So you can imagine how many problems you can work from and practice from. So we're still doing paper 1. Paper 1, guys, as you guys are already seeing, it's all about calculations. It's all about physics, things that are physical, things that you can see and touch, things that you can calculate. It's always about forces. It's always about direction. It's always about velocity. You know, that is all physical sciences is all about, okay? So this is the physics part of it. So here, we're moving on to a question. It's question 1 on that paper. It says a bird flies directly. Wait, let me just see. Oh, there's a problem that I thought was here, but it's not here. But nonetheless, we'll still make it without it. It was a very interesting problem, but nonetheless, we can continue with our Doppler effect. Okay. Okay, so we're moving on to the Doppler effect. It says here, a bird flies directly. A bird flies directly towards a stationary bird watcher at a constant velocity. We know that this one is for physical science purposes. We all know that a bird cannot fly at a constant velocity like an aeroplane, but in this case, we are allowing it to because it's physics and we're getting our point across. Okay, so a bird flies directly towards a stationary bird watcher at a constant velocity. Okay, so the bird constantly emits sound, sorry about that, at a frequency of 1650 hertz. It says a bird watcher hears a change in pitch as the bird comes closer to him. Okay, so you can already hear the difference as the bird comes closer to him. Okay, so it says the person, the listener is the person that's standing, right? So they are on a velocity of 0 because they are not moving. What is moving is the source of the sound. The source of the sound in this case is the bird that is singing or it's chirping, and it's coming directly towards the person that's standing. And it's also another thing they mention here, the bird is flying at a constant velocity. So the bird constantly emits sound waves at a frequency of this much that is written there, which is 1650. So the bird watcher hears a change in pitch. So what basically they mean here is that as the bird comes closer to the listener, there's a change in the pitch of the sound that the bird emits. Okay. So once you see a problem like that, once you hear change in pitch, change in anything, when it comes to sound, you already know that they're talking about the Doppler effect. They're not going to write on your paper that this is a Doppler effect, but you will have to recognize a question that requires it when you see it. Okay. So they say here, write down the property of sound that is related to pitch. Okay, so what is related to pitch, guys? When we talk about pitch, what are we talking about? It's easy, basically. In this case, when we talk about pitch, we're talking about the frequency, because the pitch is a frequency. This is a high frequency. This is a low frequency. So the frequencies differ accordingly. Okay. So that's what they mean when they, it's just a simple one mark question. They want to know what is the property of sound that is related to pitch, and that is the frequency. Okay. So on number 1.2, it says, give a reason why the bird watcher observes a change. A reason. Give a reason why the bird watcher observes a change in pitch as the bird approaches it. Well, in many other problems beforehand, we've always had a problem of misreading a question. They don't want to know the phenomena. They don't want to know the ideology behind the change in pitch. They want to know the reason behind it. Okay. So if they asked for a phenomena, or what is it called? The procedure whereby the birdwatcher observes a change in pitch, then we'd say it's a Doppler effect. But this one is not a Doppler effect because they want a reason. Okay, so the Doppler effect is a noun. It's a word of something that is happening. It's not a reason for it. Okay, so now they want to ask, give a reason why the bird watcher observes a change in pitch as the bird approaches him. So we can write it there as 1.2. Number 1.2, it says that there is a relative motion between the sound source and the observer. So you see what it says here. It says The reason behind it is because there is a relative motion between sound source and the observer. What does that mean? It means that either one of them or both of them has to be moving. There has to be a motion. Okay. So when there's motion, it affects the pitch. Because as you can see, if a person has to come closer to you and they're screaming your name, as they come closer to you, the scream becomes louder. But as they walk away from you, the scream becomes much lower, and which means the voice or that sound, basically that's what we mean when we talk about the pitch, that the pitch is high or the pitch is low. So that's the reason why that's the reason why the birdwatcher observes a change in pitch, because there's a relative motion between the sound source and the observer. But if they were both stationary, there wouldn't be any change in pitch. So which means that the, the 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 frequency would stay the same, the velocities would stay at zero for both of them, and we wouldn't have a frequency of the listener, because the frequency of the listener relies on one of the observer or the listener being in motion relative towards the source, okay, or vice versa, the source being in motion relative to the listener, or they can both be in motion. It depends on what the scenario state, but there has to be one or both of them that are in motion for the Doppler effect to take place, for a pitch to change, for a frequency to be observed, a change in frequency to be observed. Okay. So we're moving on to, okay, now that we've explained there, let me just erase it so that we can get to the problem at that we're dealing with. So we've mentioned there. So they say here, the air pressure versus distance graph below represents the waves detected by the bird watcher as the bird comes closer to him. The speed of sound is 340 meters per second. Guys, so you guys do, I hope you still remember your standard Doppler effect formula. Might be given in your formula sheet, but it's always good to know, so that, because if you know, then you know how to apply each and every one of them. Okay. Okay, so this is what we have, right? So FL, which is the frequency of the listener, this is the frequency of the listener, this is the speed of sound, which will always be 340. Like it said, the speed of sound is 340, and you've got the velocity of the listener, of the source, and the frequency of the source. So now they want to know, from the graph, write down the wavelength of the detected wave. So one wavelength, how do we know one wavelength? One wavelength is a wavelength that both has the upwards and negative wave. Okay. Okay. So there you have your wavelength. Okay, so this is our wavelength right there. It goes from there and then all the way there. So this is one wavelength. Okay, the distance between successive crest of a wave, especially points in a sound waves or electromagnetic wave. Okay, so this is a crest, this is a crest. So two successive crests from here to here. Okay, so this is our wavelength. So they want to know, from the graph, write down the wavelength detected. So the wavelength in this case, because it's from here going down up until here, this is our one wavelength, which means 1.3 our wavelength will be equals to 0.2. Okay, 0.2 meters. Okay, as you can see, it's in distance m, so you must write your SI unit. If it wasn't given, you'd still have to write it because you still would have had to have studied grade 12 and you'd have to know what it is. Okay, so moving on to 1.4. 1.4, I think this one will require a whole new page altogether. Sorry about that, I'm just sort of fixing my teaching mechanism. Ooh. Okay, let's keep our page neat. Okay, so 1.4, they want us to calculate the frequency of the waves. Let me just delete all of this so that I can be able to write what's given. It's going to be quite a bit of a stretchy formula. So 1.4.1, they want us to calculate the frequency of waves, of the waves detected by the bird watcher. So basically now we're coming to this formula right here because we're looking for this frequency here. Okay, so let's go to the next page and add this formula. FL is equals to V plus minus VL over V plus minus VS FS. So we already know our FS. Our FS is given there. It's 1,650 hertz. So we can write it there 1,650 hertz. And we know it's 340. And then we go there and check our okay. So here for our VL, we know that it doesn't matter whether it's a negative or positive, but it's going to be a 0 because our listener is standing still, right? They are not moving. Okay. So, and we know that for our VS, okay. Our VS is going to be minus. Oh, sorry about this. I'm doing a different problem here. Sorry about this, guys. It says you calculate the frequency of the waves detected by the listener. Okay, so we're looking for the frequency of the waves. Okay, so how are we going to calculate that? We're going to say 1.4.1. We know that there's this formula, right? Let me just make it the standard one before I substitute. We know for this formula, we've got velocity is equals to frequency times wavelength. And our frequency, our velocity there is 340, and our frequency is what we're looking for, and our wavelength is 0.2 meters. So our frequency in this case is going to be 1,700 hertz, and that's going to be the frequency of the listener. Okay, so there's many ways to kill the cat. So in this case, we couldn't have used this formula here. Why not? because we do not have the velocity of the source, and we would have two unknowns. We'd have this one as unknown and we'd have that one as unknown. So we can't use that one. Okay. So those are the tips that you guys can use. Okay. So that is our 1.4. So let's erase that and move to the next question, which is question 1.4.2. It says the magnitude of the velocity at which the bird flies. So now we are looking for Vs, because remember we do not have the velocity of the bird, but luckily we have everything else. We've got the velocity, the VL, the Vs, and the FL that we've just calculated just now. Okay. So moving on. Okay. So now we're going to come here and say FL is equals to V plus minus VL divided by V plus minus Vs. That's going to be frequency of the source. And you already have substitution here. We've already calculated this as 1,700. And this is going to be 340. That's going to be 0, so it doesn't matter. So this is going to be 340. But this one is going to be a minus. Remember from theory, guys, grade 12s, do not forget on theory, when the source approaches the listener, it becomes a negative. When it's moving away from the listener, it becomes positive. So here, our Vs is going to be a minus there. And then our frequency is 1,650. Okay. So we want to substitute because we want this to be the subject of the formula. So we're going to take this and multiply it. There's going to be 1,700 times 340 minus Vs is going to give us 340 times 1,650. Okay, and that's going to give us 340 minus Vs is equals to 340 times 1,650 divided by 1,700. So you see, guys, grade 12, everything you need to work it step by step until you get the correct answer. Otherwise, if you try and calculate according to the calculator, it's easy to make mistakes there. Always make sure that you punch in the correct answers. Okay. And then here it's going to be minus Vs is equals to 340 times 1,650 divided by 1,700 minus 340. So it's going to be minus Vs is equals to minus 10, and Vs is going to be equals to 10 meters per second. Okay. And that is our answer right there. I hope all of this is making sense to you guys. But I want to, I see our time is slowly coming to an end. But there's some other stuff that I wanted us to check quickly. So which means that I will skip some questions now and go to those ones just in case we run out of time. I hope this has been productive and you now sort of understand your mechanics, because we've done a lot of mechanic questions, okay? So these answers, I'm just going to skip them. We'll come back to them if we get time, but there's some other stuff that I wanted us to check. Okay, we've done work, energy, and power. Yeah, here we are. Let's do this problem. Grade 12 learners. You see, this is a 2014 paper, common paper. It says grade 12 learners are conducting an experiment to determine internal resistance of a battery. So now you already know the electrodynamics, okay? The learners were divided into two groups. Group 1 used battery 1 with internal resistance R1, and group 2 used battery 2 with internal resistance R2. The results were drawn as shown below. So number one, explain why the voltmeter reading across the battery decreases as the current increases, okay? The voltmeter reading across the battery decreases as the current increases. Use appropriate equation in physics in your explanation, okay? So let's see. So here we have it there. It says 3.1.1. It says EMF is equals to internal resistance plus internal resistance, external resistance plus internal resistance. So when the current increases, IR or loss volts increases, okay? As you can see, it's according to this formula that is here. So IR, external terminal voltage potential difference, will also decrease. So you can just write down that formula of EMF and it will be able to explain how, just by writing it there. And you know, if you increase the current on that part, it's going to decrease the EMF or it's going to increase it. So make sure you understand it. See, so this is a simple 2 marks. Actually, it's 3 marks because it's 1 for the formula, and then you've got 2 marks for the explanation, the part that says increases and the part that says decreases, okay? So which group 1 and 2 uses a battery with a greater internal resistance? So, okay, so it's likely this group 2, right? There's a greater internal resistance. Why do we say that it's got a greater internal resistance, guys? Because look at these two. They both have internal resistance, right? They both have voltage and current, right? But look at the resistance. Remember what they say about resistance. V is equals to I times R. And R is equals to V over I, right? So what does this mean, guys? It means that when we look at the current alone, let's look at the current alone in this case, because I want us to work from this one. If the greater the resistance, the lower the current, right? So the resistance is inversely proportional to the current. So which means that as the current increases, the resistance will increase. But if you check this two, which one has the lowest current? Group 2 has the lowest current. Why does it have the lowest current? Because it's got the lowest current because the resistance there is increased. Okay, I hope it makes sense to you guys. So that's the reason, because it's 2 of them. They both start at the same point. But if you check, group 1 has a higher ammeter reading than group 2. So meaning that group 2 has a higher resistance. That's why it's much lower than the one on group 1. Okay. But no problem. I think we'll still do some more problems of paper 1 next week, seeing that we still haven't covered everything that we need to cover. So on 3.1.2 it says, use the diagram to determine the EMF of the battery used by the learners in group 2. the EMF of the battery, it's 12, right? You see, it's 12 volt. Because how do you check? You check it here from where it starts. Just because the battery decreases the current doesn't mean that it's not 12. It's still 12 because this is where it started. Wherever it starts from, that is your EMF, okay? Electromotive force, okay? So it says on B. So that's your simple 1 mark that you can take just by writing the 12 volt. So it says on B, internal resistance of the battery used by learners in group 1. Internal resistance of the battery used by learners in group 1. Okay, so here you can take anyone, hey? You can take 10, you can take, okay, let's see. You can have V1, V2, V3. No. R1, R2, R3, R4. And that would be, remember we said R is equals to V over I. So in this case, we'd have 10 divided by, current here would be 0. So this one will be 0. And then for this one here, it's going to be 8 divided by 1. Because you see, it's on the 8, but the current is 1. Okay? And then, oh, let me see first which group we're working with. Used by learners in group 1. I'm still on the right path. Okay, and then we'll have also this one here, which is going to be 4 divided by 2. So this one's going to be 8 and this one is going to be 2. So basically this is how the gradients work, okay? So how do they do it here? So you see the gradients A and Y. So what they've done here, the change in Y is equals to the change in X. So 4 minus 8 and 4 minus 2. Okay, so this will be y2 minus y1 over y1. You see here they are. Let's go back to the graph. So you have 4 there. There's our 4 there. So you're going to have it, because you calculate it like this, you're going to have R2 as 8 and 2. So which means that it's going to be resistance is equal to change in Y divided by change in X, which is equals to 4 minus 8 divided by 4 minus 2, and that will give you that answer that we have there. So it's going to be a 2 ohms. 2 ohms resistance, okay. Okay, so we're done there. So we're moving on to 3.1.4. It says, if the internal resistance of the battery was neglected, draw a sketch graph to show the shape of the graph when the voltmeter reading is plotted against the ammeter reading. Okay, so what do we know about velocity and current? What we know about velocity and current, remember, V is equals to I times R. So an increase in velocity is an increase in current. So which means that the more they increase, start at 0.12. Just trying to go back to that page. Yes, if you had to draw it like this, you can see there that the velocity there is a bit constant as this increases, okay? So if you had to make this the subject of the formula, then you'd have a straight line because it would show that it's at constant velocity.